This is a very happy day in Calculus 2 because we're going to start talking about infinite series. This chapter 8 is really a third of all the new material we're going to talk about. Chapter 7 was on integrals, 8's on infinite series, 9's on polar and parametric, but a good portion of what we're going to do this semester is infinite series. I'm going to give you a second, so pause this and copy this little Venn diagram that I've got already ready. Pause. Go ahead and pause. Okay. So first thing you need to do, if you're not convinced so far, let me convince you that infinity terms can actually have a finite sum. All right, if you've learned about geometric series in Algebra 2 or in stats or some other class, you've learned probably about infinite geometric series, and this is just one style of a series where you can keep adding on terms forever and never go over a certain amount. An illustration that I always like to use is, let's just imagine you've got a 10-gallon bucket, and one day you come in and you pour 5 gallons of water into the bucket. And then the next day you come in and you fill up half of the empty space with water, and you add 2.5, and then there's going to be 2.5 left over of empty space, and the next day you pour in half of that empty space, so that's 1.25, and the next day you pour in half of that empty space, and half of 1.25 is 0.6. I don't know what half of 1.25 is. To go to the calculator. I'm embarrassed right now. Half of 1.25 is 0.625. I knew that. It was just a test. 0.625, and so on. So you keep on adding these numbers in forever, and you will never overflow this 10-gallon bucket. So this infinite series of numbers, it's going to turn out to be the kind of series known as a geometric. It converges to 10. Now, I'm not talking about the sum or the terms. The terms converge to 0. And in 8.1, we talked about convergence or divergence of terms. I'm talking about the sum converging to 10. Because if I kept this pattern going on forever, I will never go over 10. So back to this Venn diagram. We're going to learn basically 3 rules today. And here's the most important one. Any series whose terms do not go to 0 will never converge, okay? So somewhere outside of your bubble, write nth term test for divergence. And here's an example. 1.1 plus 1.01 plus 1.001, and so on. If I kept adding these terms up forever, the terms themselves are not approaching 0. The terms themselves are getting closer and closer to 1. So I have an infinite amount of terms that each of which is at least 1. Then I have at least infinity because I have 1 infinity. So the easiest way to check for divergence is just to see, do my terms even go to 0? Because if your terms do not go to 0, then your series is left out of this exclusive club of the terms that do go to 0. Once they do go to 0, then we're sorting out which ones converge and which ones diverge. But in order to even have a chance at convergence, the terms have to go to 0. So anytime you see, here's one example. Another example would be something like a sub n equals, let me rewrite that. We're going to start using a different notation. We're going to start using sigma notation. So this will be the sum as n goes from 1 to infinity of, let's say, 2n squared plus 1 over 3n squared minus 3. This series, as n gets really, really big, the terms themselves are approaching 2/3. The plus 1 and the minus 3 are meaningless. The n squareds are all that matters. So the limit of these terms is 2/3. Therefore, this little symbol, 3 triangle of dots, means therefore. Therefore, the series diverges by the nth term test. Okay, and that just means if the terms don't go to 0, there's no way the thing can add up to anything other than infinity. What if the terms are approaching a half? If you have infinity halves, then you basically have infinity, because half of infinity is still infinity. So that's your first kind of screening process. You look at this series and say, do the terms go to 0? And if not, just stop right there. Say, these terms are not going to 0. They're going to something else. Therefore, the sum has to be diverging. It has to add up to infinity by the nth term test. Now, listen to this. By far, the most missed, or the biggest mistake in this chapter, or this, yeah, I guess really the whole chapter, is trying to use the nth term test backwards. I can say that the terms are not going to 0, therefore this series is divergent. What I cannot say is the terms do go to 0, therefore it converges. Like 1 over n, for example. All right, this series is 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, and so on. Those numbers are getting smaller, 1/5, 1/6. The millionth term is 1 over a million, which is approaching 0. However, you cannot say that this series converges because the terms go to 0. The common mistake is to say the terms approach 0, therefore the series converges. It will happen. It happens hundreds of times every year, and it will happen this year. Just don't let it be you that it happens to. Just because the terms go to 0 doesn't mean the series converges. If the terms go to 0, now I am a part of this big outer circle of ones that do go to 0, and then I have to sort it out. Is it going to be over here, or is it going to be over here? Okay, so let's start with that. If it passes the nth term test, then you can say it's part of this bubble, and then you have to decide, does it converge or diverge. I'm going to come back and fill in on the diagram, but before that, I'm going to give you the two styles of series in this topic, in this section. A geometric series basically is a series where you multiply by a constant to get from one term to the next. And the general form for a geometric series is this. The sum as n goes from 0 to infinity. This is one example of where we usually do start with n equals 0 instead of n equals 1 of a times r to the n. So the reason we start at 0 is so that our first term can be a, because when n is 0, r to the n is 1, and we're just left with a. And sigma means sum, so then I add on to this the term I get when n equals 1. When n equals 1, I get a times r. When n equals 2, I get ar squared and ar cubed. So you can see that to get from one term to the next, I multiply by r each time. Okay? For example, three times 1/2 to the, nth. All right, here's a geometric. It fits right into the format. This is, I wrote 2 again, excuse me. n, n. 3 times 1/2 to the 0 is 3. 3 times 1/2 to the 1 is 3/2. 3 times 1/2 squared is 3/4. 3 times 1/2 to the third is 3/8, and so on. To get from term to term, I multiply by 1/2, and so on and so forth. So, convergence or divergence. There's a simple rule for geometric. And make sure you get this down, definitely. If R is between -1 and 1, not inclusive. I'm not going to include -1 and 1 in this rule, but if it's anything between -1 and 1. Another way to write this would be the absolute value of R is less than 1. Then it converges. All right, my bucket example was a perfect example of this. My R value there was 1/2, because I went 5, 2.5, 1 1/4, and so on. And it never went over 10. Also, if you noticed on the Venn diagram, a lot of times you can just say that it converges, all of this area out here. Occasionally, you can actually see what it converges to in this area here. So geometric is one of the few instances where I can actually add up the convergent series. So I have a little formula for that. It converges, let's see, also, it converges to, I like to use S infinity for the sum of the infinite. They just use the sigma notation in your book, but it's A over 1 minus R. The first term over 1 minus R is going to give you what it adds up to. So just to kind of confirm that this formula works, if the sum of the infinite series is A over 1 minus R, A is the first term, which is 5. 1 minus R, R is 1/2, because that's what I multiply by each time. That's 5 over 1/2, which is 5 times 2, which is 10. And that was a 10-gallon bucket to start with. So you can see that the formula does, in fact, work. So back here, on series that we can actually sum up, we have geometric with the absolute value of R less than 1, and the sum is equal to A over 1 minus R. Not often can you actually get an answer like 10 on the bucket question. Usually you can just say, yeah, it converges, but I don't know what to. And this is one of the cases where you can actually tell what it converges to. Okay? Last one is going to be a telescoping series. In telescoping series, it's just kind of a special case of series where terms just happen to fall out of the series. I'll show you what I mean. 1 over n minus 1 over n plus 1. All right, that's my series. If you just start to write out some terms, and usually you can tell a telescoping because it'll have two terms being subtracted from one another. When I plug in 1, I get 1 minus 1/2. All right, my next term when I plug in 2 is going to be 1/2 minus 1/3. My next term is going to be 1/3 minus 1/4, and 1/4 minus 1/5, and so on. And you can kind of see how this thing just sort of collapses upon itself like an old school telescope. The negative 1/2 and the positive 1/2 cancel. The negative 1/3 and the positive 1/3 cancel. Negative, positive, cancel. And that happens all the way out to infinity. And this thing ends up adding up to 1. So this is kind of a special case. It's a rare one, but you should be aware of it. It is actually a real thing. So in the bubble, for series that we can actually sum up, add telescoping. So for this section, The most important rule of this section is the nth term test. If your terms do not approach zero, like this down here, the one in red and the one in green, you can immediately stop and say divergent nth term test. You will never say this series converges by the nth term test. There's no such thing. Because if it passes the nth term test and the terms actually do go to zero, this is not the case. You don't say, hey, my terms go to zero, therefore my series converges. Your terms converge to zero, but your series may or may not converge. At that point, you know you're in the big bubble and you're just trying to figure out where that series goes. And through each of these next several sections, we'll learn a different style of series and figure out which half of this bubble to put it on. For now, these two that go on the left-hand half are also within this bubble that we can actually add up. So some of these you might be asked to tell, does it converge, and what does it converge to? All right, so that is section 8.2. This one's just going to be a one day. We might take more than one day to work on it in class. We'll just see how the timing goes. But I hope you're happy, because this is a wonderful section that we're starting. This chapter is good. Infinite things that add up to finite amounts. It's always fun to talk about. So I will see you in class. I hope you enjoyed it. Make sure you have a nice big Venn diagram to add on to as we go. I'm out.